Okay, so our next talk will be by Will Rosenbaum, and he'll be talking about bias reduction for sum estimation.
Awesome, thank you. Right, so like Sesh, this is my first time talking at MIT. And also like Sesh, this is my first in-person workshop since COVID started. So I guess that's the session of new experiences. So yeah, so I'm Will Rosenbaum. I'm from Amherst College, which is not to be confused with UMass Amherst, which is the big university down the street from where I am. And I'm going to talk about joint work with Talia Aden, Jakob Howen, Sham Narayanan, and Jakob Tetik. Late breaking news, this finally showed up on arXiv. So if you want to look at the paper, it is there. Okay, so yeah, also not to just keep comparing things with Sesh, I love about his talk that you just have this kind of sequence of miracles of interesting things that lead to interesting problems that have interesting solutions. My talk is a little different in that I only have one miracle, and hopefully you guys will forgive me for that. So I'll give a little bit of motivation and talk about kind of the general setting of this problem. I'll talk about this problem of bias reducing sum estimation, and then I'll talk about lower bounds. So that's the plan, and we'll see how it goes. Okay, motivation. So I want to start really concretely with a really basic statistical question. So imagine that I have a population of n voters, say, or n entities. I don't really care what they are, but we'll call them voters for now. And they're just trying to decide some binary proposition, yes or no. And each one can vote yes or no. And our goal is just going to be to estimate the number of yes votes. We want to do some sort of prediction. And maybe we know something about the expected margin of victory. Say it's going to be a tight race. It'll probably be in the neighborhood of 3%. So we want to estimate the vote, the number of yes votes, say, to something a little bit less than 3%. So here's my picture. I have a bunch of voters, say blues or yeses, reds or nos. And the typical assumption in statistics and in a lot of our work as well in terms of sublinear time algorithms and things like that, which I am foreshadowing with this word unfounded, is that we can sample voters uniformly at random, or even that we know the distribution from which we're sampling voters. So this is kind of the setup. And so this is really classical work in statistics. So the procedure is that you would use classically is this easy estimation. You just sample n voters. You associate a random variable xi with the ith sample that you get. Say it's 1 for a yes, 0 for a no. And we just want to return this kind of empirical average that's rescaled to the number of samples that we do, or the population size. And the guarantee, like this is just a straightforward application of Chebyshev's inequality, is that if we want to get, say, an epsilon n additive error with some constant probability, we can take some function of epsilon, I think it's epsilon to the -2 samples, and things will be good there. Okay, so this is easy classical stuff. And so here's an example that I totally didn't just make up the data for because it works, but let's say we have 108 samples in that picture and we choose m is 20 is sufficient. So we sample the voters, we get, in this case, the exact average or the exact sum is 58. We apply our estimator and we get a value of 59.4, and we predict that the yeses win. Okay, that's fine. Okay, but I kind of question this assumption, like, why are we assuming that we know precisely the distribution from which these samples are being made? And where are we using that assumption? So essentially the place that we're using that is in this coefficient of n here, saying that all samples are equal. I'm equally likely to get everyone, and they're all going to weight equally in the sum that I'm predicting. Okay. But this is not typically going to be the case, right? Like there might be some underlying bias in how I'm collecting these samples. The biases, they could be random, or they could systematically favor yes or no voters. I might be more likely to sample yes voters. I might be more likely to sample no voters. And if I'm looking at a very small portion of the inputs, maybe I can't even determine which way the bias goes. So the true distribution that we're sampling from might not be known. but maybe it's close to what we know. We have some prior distribution. We think, okay, we're sampling approximately uniformly, but there's some bias in there. I don't know how much it is, but I can bound how big it is. And so one way we might quantify this is to say that our distribution that we're sampling from is close to uniform in this kind of strong pointwise sense. So maybe no voter is more than 10% more likely than uniform to be sampled, and no voter is more than 10% less likely than uniform to be sampled. In this case, I'll say that my sample distribution has a bias of 10%, or a relative bias of 10%. Okay, so this is maybe a more realistic assumption, but then what happens if we weaken our sampling? So maybe my samples are biased in the yes favor. Then before I got an answer of like 59 in my empirical sample, here it bumps up my sum to 65-ish%. And so yes is still predicted to win. On the other hand, if the bias is in the no favor, I now am predicting that the yes vote is going to lose. And I don't really, if I'm just kind of aggregating the sum of the collected samples, I have no way of distinguishing what is really going on here. Okay, so the question is, can we do better? Can we estimate this sum up to an additive error of, say, 2% using a sublinear number of samples? So the naive estimates would give us an error that's proportional to the sample bias. And we want to do something better than that, but we don't want to have to see everything in order to do that. And our work answers this question with an exclamation mark that yes, we can. And so this is a special case of our results. We kind of have a very general estimator, and then I want to apply it just to the context of this example. So if our sample bias is, say, 10%, and we want to get a 2% error on the sum that we return, we can do this, we can achieve this error using square root n samples. So much more than constant, but much smaller than linear. And more generally, if I just have 0, 1 random variables or 0, 1 values that I'm trying to estimate the sum of, and I have some upper bound on the sample bias, I have some desired approximation factor epsilon, I form this k, which is the log of epsilon over log of gamma. So the k is just the power of gamma that I need to get epsilon. And then the number of samples that I need is 1, or n to the 1 minus 1 over k. And then we show that this sample complexity is actually tight. And we'll see kind of how weird it is that this sample complexity is tight because of this ceiling function. Like it's not uniform, but it is tight, which is a kind of strange thing. Okay, so how does this fit into the bigger picture? So I talked very concretely about a kind of toy problem from statistics, but this is something that arises in kind of sublinear time algorithms and distribution testing, property testing, statistics all the time, where we assume that samples can be generated exactly from some distribution. And this is, I don't think, a well-founded assumption in practice. And so the kind of general questions that we were trying to address with this work, and this is, I think, just a very first step in this direction, is under what circumstances do having noisy samples suffice when we don't know something about the noise? And there's some results related to distribution testing showing that certain things will certain algorithms remain true, even if your oracle that's supplying you samples is lying to you a little bit. But as far as I know, there's not like a systematic study in this direction yet. And so if I do have noise in my samples, what's the algorithmic cost of coping with this? Can I correct the sample bias? Okay, so what's kind of the more general setting of our work? So in the setup, we have a universe of n elements. I'll just call them 1 through n. And each item has an associated value that I'll call xi. And we have a known probability distribution that is what we think we're sampling from. And then we have a q, the true sample distribution. And we assume that q is pointwise close, pointwise gamma close to p in the following strong sense, that every element is sampled with approximately p of I up to this factor of 1 plus or minus gamma. And our goal is to sample or to estimate the sum to within additive error. So I just have kind of two error parameters here because, well, we'll see that they come from different places. But one is this multiplicative error that multiplies mu plus, so the sum, but it's just the positive sum, so the sum of the absolute values. And then we have this kind of absolute additive term that arises from the variance that there's nothing we can do about. And again, what's, I guess, kind of unique about what we're doing in this work is this following piece, that we're assuming that epsilon1, this multiplicative factor, is much smaller than the bias of the individual samples that were given. Okay, so the classical setting, this is studied in statistics, so this goes back to Hansen and Hurwitz from the 1940s, and they give this estimator that says we do just a slight generalization of what was suggested in the example, where we just sample a bunch of elements and then we return this is our estimate. So we kind of take an average over the samples, what each sample contributes to what we think the sum would be. And Hansen and Hurwitz consider the case again just where P is equal to Q, and they show this is an unbiased estimator. And in general, we show, or it's straightforward to show, that the bias is at most gamma times mu plus, the positive sum of these terms, when Q is pointwise gamma close to P. But again, we have this gamma in front, and we want something strictly smaller. Okay, so this brings us to bias reducing sum estimation. So our idea, the first idea, is to apply this Hansen-Hurwitz estimator instead of to individual samples, applying it to H-wise collision statistics. So what is an H-wise collision statistic, or what's an H-wise collision? It's just a bunch of indices that I sample, H indices that I sample, that I'm resampling the same index H times. So that's an H-wise collision. And we can use exactly the same estimator as Hansen-Hurwitz, except apply it to the collisions, H-wise collisions, rather than the individual samples. And this is the expression that we get when we do this. So M choose H is the maximum number of H-wise collisions we could get from H samples. Yi is the number of times that I was sampled. So this first term here is just the number of H-wise collisions that we see involving I. And then this term pi to the minus h, so that's 1 over the probability of getting an H-wise collision involving I, assuming that they were sampled from P instead of Q. And then we just have our xi term that we're using to form the estimate. And so in the case when H is 1, this is exactly the Hansen-Hurwitz estimator. For general H, it's something different. So this is our idea, is to look at this thing. And here's the letdown. The H-wise collision estimators alone or individually are no better than Hansen-Hurwitz. The bias is actually larger, the variance is larger. They seem to be completely unhelpful. But an appropriate linear combination of these things can actually force the lower order terms in gamma to cancel out. So if we do a little bit of linear algebra, we can define this bias reducing estimator. So here's my H-wise collision estimator. And I just take this linear combination of those. And the main result that we prove is, or the main upper bound result, is that this bias reducing estimator, zeta k, has bias at most gamma to the k times the positive sum. So we're reducing the bias from gamma for Hansen-Hurwitz to gamma to the k for this bias reducing estimator. And we also bound the variance of zeta k. So this is actually the most technical part of the paper, is bounding this variance of zeta k. All right, and we need that for our algorithmic applications. All right, cool. So any questions up to this point? All right. So this is the magic trick, is that this works, and this is the only magic trick. So here's a consequence, is if we look at the special case where P is the uniform distribution, all values are 0, 1, so our original example, we can take this number of samples. So again, the part that I kind of care about most right here is this, which is another way of writing, ooh, this should be a capital N, n to the 1 minus 1 over k. So if we take that many samples, then we can estimate mu to an additive error, gamma to the k times mu plus epsilon 2, where we get to choose our epsilon 2. And this var HH is just the variance of the Hansen-Hurwitz estimator. And again, this is a term that there's really nothing that we can do about because, well, yeah, for reasons. Yeah, of course.
Yeah. So just to get some intuition for what's going on, is it something like shows your samples? There are some individuals who make a sample multiple times, and so you would kind of weight their answers differently and then take the average?
Exactly. Yeah. So we're just kind of weighting the answers differently depending on how many collisions we witness. So K again is this, K is the ceiling of log epsilon divided by log gamma. Yeah. Thank you. That should be on the slide. Well, I don't want to think of it as a constant. It is a constant, but yes. I want to think of, I don't know, my way of appreciating this is maybe thinking of gamma as a constant and epsilon is the thing that we want to control. That's maybe the variable. So yeah, in our original sample, our gamma was 10%, 0.1. And we wanted to have an estimate within 2%, so the total error should be 2%. So we can pick our epsilon 1 to be gamma squared, which is 0.01. We can pick our epsilon 2 to be this other additive term that we get. So we get another 0.011% of n for our second term. And this gives us our overall error of 2% of n. And our m, this term, is again square root of capital N. Okay. So that's our kind of chief consequence or way of kind of understanding the value of having this estimator. So what can we say in the other direction? Well, we have lower bounds. Okay, so our lower bound is again for the setting of this concrete example where P is uniform, Xi is in 0, 1. And our main result is as follows. So suppose that we have an algorithm A that guarantees that for any desired epsilon, and for every distribution Q that's pointwise gamma close to P, or which is uniform, so pointwise close to uniform in this case, our algorithm returns an epsilon n additive approximation to mu with some constant probability. So for every positive integer k, there is a constant ck minus ck, which is less than 1, so that for epsilon much smaller, a bit smaller than gamma to the k, we need actually more. So we have this n to the 1 minus 1 over k plus 1 samples are necessary. And this is where this ceiling function in our complexity actually comes into place, because this looks bigger than n to the 1 minus 1 over k, right? But we're multiplying by something that's less than 1 here. So when we take the ceiling, we actually get k plus 1 in our algorithmic complexity. So I want to look at a picture of what this looks like. So this is the sample complexity. So on the horizontal axis, I have log epsilon over gamma. And again, I think it's instructive to think of gamma as being a fixed constant, something that we don't have any control over, and epsilon is our variable, something that we have that we want to control. And then on the vertical axis, I have the power of n in our sample complexity. So the red lines are the lower bound, the blue lines are the upper bound, and the black lines are where the lower and upper bounds match exactly. So kind of the width of this region where the lower and upper bounds match exactly is determined by these constants ck from the lower bound here. So the larger these are, the closer they are to 1, the wider these regions are where the lower and upper bounds match. And so we have this really strange complexity from looking at where we have these black lines, because these kind of demonstrate these islands of stability, where if I perturb epsilon a little bit, it doesn't change my asymptotic sample complexity needed to estimate the sum. But then in these gray regions, there's something going on where any small perturbation in epsilon will give me an asymptotic increase in the sample complexity. So we have this very non-uniform complexity as a function of epsilon, where sometimes it's kind of rapidly increasing, and sometimes it's stable. And so this was a surprise to us that, I mean, one, that this is the answer, and two, that all of the math worked out to give us this answer. So yeah, I don't know. I don't know if this this picture doesn't look that interesting in terms of pixels on the screen, but like I think the interpretation of it is to me, it seems kind of profound. So yeah, this is something that was a surprise to us. Okay, so I think that's the main points that I wanted to make. But I wanted to talk about a couple of open questions. So the first question is to kind of tighten these values of CK. I don't like these gray regions where the upper and lower bounds don't match. I mean, that's complexity theory, right? We don't like things that don't match. So if we could improve the analysis, get better values for these CKs, we could kind of see how wide these islands of stability are. And maybe there's something interesting that goes on in between, like maybe the real answer is like this, right? I have no idea. But I don't know, it would be kind of wild if the real answer was the upper bound, that like the complexity is really a step function. I think that would be really interesting to know. So another question that we had, so this is kind of correcting bias from samples for the purposes of estimating a sum. But in general, we might just want to correct the bias of the samples in the first place. So can we kind of adapt this framework to just say, okay, you're giving me samples with 10% bias. I want samples with 1% bias, with 0.1% bias. Just run a black box algorithm and give me those samples. I think that would be a really cool thing. I'm not convinced that this is not easy. Maybe it is, and we need some time away from thinking about the analysis for a while. But yeah, this is a potentially, I'm not going to commit to ink, but I'll say maybe it's a doable question. And then a kind of more general question is, you can kind of look at all of the literature on sublinear time algorithms and say, okay, which of these results are robust to noise in the distribution? How can they be made robust? What is the algorithmic cost of making them robust? And this is something that, this was actually the question that Talia and I were talking about when we kind of started down this line of work. And I still think this is a really interesting question because it's annoying. Like a lot of times you'll read a result in a paper that you want to use, and then you say, but they assume uniform samples, and my subroutine only gives me approximately uniform samples. And so I have to go through their entire analysis and argue why their analysis doesn't break. And it never does. But we would like to have conditions under which the analysis doesn't break, or just have some kind of black box, or maybe we just all agree as a community that we're going to start assuming that things are only approximately uniform or something like that. And that's the proof that it ultimately gets written up. But at the end of the day, I think this is an interesting thing because I think that knowing exactly the distribution from which your samples are coming from is not normal. I think that the normal thing should be that we have some estimate of what the distribution is, and then we go with that. Okay, so these are the questions. This was a little bit more philosophizing and maybe less technical, but thank you for coming on the journey with me. And yeah, I'll open things for questions.
Thank you. Yes, Peter.
I can just ask.
I can repeat.
Yeah. So how crucial is the assumption that like gamma is smaller than 1?
So we absolutely need it. So if we don't have gamma smaller than 1, we have no guarantee over what the distribution is anymore.
Well, you don't have a lower bound, but you have an upper bound.
So let me see. I mean, because we have this pointwise estimate, what slide am I looking for here? I mean, if gamma is 1, oh, I see. So yeah, you're right. Then I still do have that. We actually didn't think about that in the analysis. We were kind of thinking of gamma as being small.
Otherwise, you just have people who never answer your survey. There's no way to figure out what their actual needs are.
Yeah, and so this is actually another question, or maybe a criticism that some of you might be thinking in terms of this definition, is that it's much more standard to use like L1 distance, total variation distance or something. And yeah, the issue there is that you can throw away an entire epsilon fraction of your inputs and you're still within total variation distance epsilon. And then you get no guarantee on your estimate of the sum because maybe you're throwing away all of the non-negative terms or something.
Most common to have the left-hand side within a CFI divided by gamma, and then
Yeah, I don't, yeah. It's, yeah, because then it's like, that's what I would mean by like a multiplicative 1 plus epsilon or 1 plus gamma. I don't know why we did it this way. It happened in one paper and then it happens in subsequent papers.
So one question I had was, I don't know if this is even, seems a little ill-posed, but you're sampling with replacement, which is fundamental to how your estimator works.
Yes.
Is there a way of understanding this of sampling without replacement? Like, is it like over permutations of the samples or?
Yeah, so I don't know of any way in which you would kind of make sense of this without replacement, because we really are crucially using these combinatorial facts about sampling collisions and the probabilities associated with them. But yeah, that would be an interesting question is like, yeah, if our model is that we're only sampling without replacement, like, does this work at all? Like, is there a way to finesse the details? Maybe, I don't know.
The only information you could possibly learn that is the number of yes answers, the number of no answers. And then if there's a bias to return one answer or the other, there's no way.
Yeah, I mean, certainly, yeah, I think I find this probably convincing.
Okay, so if there are no more, oh, there is.
So I had two questions. I asked my second question first because it's related to that one.
Yeah.
I think it's interesting to study cases that you have some additional information. For example, you have some other knowledge about some other distribution over the population. For example, there are some estimate of their, let's say, ethnicity or some other factors.
Yeah.
In that case, it becomes possible that without replacement, you can get more information or you can get better results, I think.
Potentially.
My first question is, you're assuming that you're sampling items from the same distribution, right?
Yes.
So if you change that distribution, it would be an interesting question if you keep the distribution still within these gamma bounds and then see whether you can get anything or not.
So like changing, so we fix P and then Q is just kind of varying.
So if the error gamma is coming, for example, because the people that you send to gather the information, there is some noise in that process,
Yeah.
and that noise changes from today to tomorrow, then you cannot assume that this is the same distribution.
So I think because my gut feeling is that because these constraints are convex, that if you kind of let things change, you're taking a convex combination of different distributions, and so you should end up still in this set. So I think everything should work out in that case. Ah, good. Well, but it doesn't because my P is still the same in all of them. Oh no, so as I understood it, P is fixed. And then the Q is changing from day to day. So but if it's, but if they're all at most 1.1.
But it's not going to be a convex combination of collisions.
It just seemed that there might be some problems with the calculations.
So,
I cannot be sure.
I don't want to think out loud, as they say. But yeah, that is a good question as well. If there's some natural way that we can just kind of, that everything fits in.
Thank you.
Thank you.
Okay, so let's thank Will again, and